Okay. Yes, that's it. Yeah. So as we said in the at the end of the last meeting, I think we stopped at the device numerical batch. And device, you can, for example, as I said before, if you design the solar cell system, you need to design from the photonic point of view and from the electronic point of view. So, for example, you need to design the solar cell that trap that have the most highly efficient that trap most of photons from the sun. If you actually design this solar cell, you can complement your design into the electronic one. For example, these photons excite more electrons to generate electricity. So there is the part of this electrons you can simulate it using device. So, and you can transfer, if your system has the heat degrees of freedom, you can use device as well. So device for the heat transport and for the charge transport. It depends on your on the parameter of your photonic device. For example, what is the example of the heat transport? If we create a modulator like a Mach-Zehnder interferometer, and we need to modulate or manipulate the light, so we can manipulate it using temperature, you know, to change the mood or the characteristic of the light in one side. You know, the Mach-Zehnder interferometer like a Y splitter, and if you inject the light from the input, the light will separate into two different two different waveguides. The first one will has this modulation option that you can heat this waveguide to modulate the light, and you can create this optoelectronic device. So you can use device and in the charge and the heat, and you can find a different time domain for the 3D nanophotonic device and mode for photonic integrated circuits, mainly waveguide cells. So there is something called interconnect. You know, interconnect, like if you remember when we studied at the earlier years in our university in electronics or physics, you know, I cannot remember the package itself, but there is a lot of software that you can drag and drop diodes and wires, you know, copper wires and diodes and resistance, and you know, to create electronic circuit. I believe that all of you working about that in his university journey. So interconnect like this software, but for the photonic integrated component. Like what? So if we are design finite difference time domain, or actually a nanophotonic, and we need to extract this design to be like a package of this design, and we need to create a circuit. So the first component will be the solar cell from the photonic point of view, and the second one will be the solar cell from the electronic point of view. For example, I'd like to give you like this. You know, this is. Can you remember? Can you see anything like that before? I believe that, for example, this is. If you create a Mach-Zehnder interferometer, you need to simulate every waveguide, the Y splitter itself, in the mode, and then the waveguide itself, because this waveguide may has different characteristic. For example, this waveguide may be a photonic crystal waveguide. So you need to, yes, you need to simulate this waveguide separately and make it in a package, and then drop it in the interconnect solution to make this circuit. And of course, you need to add the S parameter. You need to simulate the losses in the system. You know, the losses can be happened during the manufacture process or whatever. So all of this need to be simulated accurately. So you combined all of the simulated photonic component from different packages into interconnected packages to create this circuit. Okay, so and all of you need to know that. And actually, this is a finite difference time domain GUI. You need to, there is a photonic device here, and you can add different components, and you can add source like that. You can add a circuit. No. Yes, you can add a structure, add a server region, add a source, for example, like the light source, the laser source, and you adjust the specification of the laser. For example, as I said before, you need to set the wavelengths to be 1.55 micron, and to be add the monitors. And this monitors is to for example, if we design a waveguide, the input will be a laser guide in one side of the waveguide, and I need to monitor the output of this waveguide. Why I need to do that? Because I need to measure the loss, I need to measure the characteristic of this, of the output light and whatever. We can do that using monitors, and of course we can add material properties. For example, this with the waveguide, or the waveguide actually is made from the silicon on a silicon dioxide substrate. So all of this materials are pre-defined in numerical itself, but you can add new materials to work on it, and you can run simulation and make analysis on the export results. And this analysis actually your rule, the role of machine learning team and the role of quantum machine learning team. Why? Because we take the data and we can create, and you can apply different machine learning models on this to predict the behavior of this designed designed photonic device. So, for example, if regarding to our back to our yes, we're at the paper. Yeah, back to our papers here. We design what? Yes, we design optical photonic crystal fiber. So we designed that using mode and numerical, or maybe we can use finite difference time domain as well in the numerical package, and we generate the data. And the data we need to optimize the waveguide itself. So there is a lot of parameters. So if we get more complicated photonic device, we have more parameters, of course. So we need to optimize all of these parameters to obtain the most optimized output for our design. So, for example, here we need to, as I said before, again, we need to optimize the chromatic dispersion and whatever, and the loss and the reflective and effective reflective index. So we need to optimize all of this in this design at different structure. So we can do that in different ways. We can do that using particle swarm optimization. We can do that using a sweep analysis. Sweep analysis is taking a lot of time because, for example, in D input, you can sweep from 1 to 1.6 micrometer, a step of 0.2 micrometer. If we want more smaller step size, it takes a lot of time to generate this data. So we can also, of course, use machine learning model to describe. Okay, if we use the input as kaza as 1 micrometer, and we use different wavelengths, how can we predict the behavior of this photonic device? So it's all about to save time and save cost. So we can use a lot of different methods, but the most important thing that we need to make it in most accurate way. So why we use quantum? It's a very important question. Why mainly we use even classical machine learning in this? So if we cannot add this accuracy parameter, I think it will be useless. So, and actually the amount of data is significant, and the quality of data is significant, but I can assure you that the quality of data is good because we use a reliable software package. Even if it's a numerical or COMSOL. But of course, if you wow, you didn't see this. Did you see this PDF yet? I thought that you didn't.
No, it's visible. It's clearly visible. I can see your mouse cursor moving.
Yes, great. So back to our presentation here. Yes. Oh. Okay. So back to our presentation, I think the contribution for the team of the classical machine learning and the quantum machine learning is all about. Maybe I suggest the CRISP-DM framework to you because actually, if you apply, for example, download available data from some of the provided papers, and you need to apply the same models, the artificial neural network or SVM or whatever, you need to document this. Yeah, of course, you can apply different models. And I think you have an intuition about that. So you need to document all of this, all of your steps in the from the perspective of the machine learning pipeline. I'd like, sorry. So, for example, of course, you need to understand the business, what we are about to do in this project. Actually, we need to design a biophotonic sensor. And actually, we can provide you, and I think we will do that in the photonics team. We can provide you not only one biophotonic sensor, we can provide you with the data from different biophotonics design. And I need to take this confirmation from the team of photonics. If we can do that, I don't know if we can do multiple design biophotonic sensor, and we give you the data from this. Yes, Muhammad, I will be with you right now, but I will finish this point, and we can open the discussion between all of us. This is the last thing. So the CRISP-DM framework, for example, you need the data from the first biosensor, the first biophotonic sensor, and you apply different models. But of course, you will process doing some manipulation about the data, of course, in the data preparation stage. All of your what you are about to do in the data preparation stage, technically, you need to document it, to document from different biophotonic sensors. And if you are applied to apply different models, you need to ask yourself why I use SVM, why I use, for example, random forest, whatever. I just give you an example. Why I use this? What is the intuition behind using this model? What the comparison between different models, and whatever. So, and of course, and this you can do that in the evaluation process. All of this you need to do every single day, or actually, if you need to apply different models, basically. So I'd like to back to our architecture. Of course, this is a very simple architecture because we are at a starting point. So this architecture, every team needs to has his own architecture. So in the first block in the design photonic device, okay, we use this device. Why? We simulate another device. Again, why? What our expectation from implement this or that? So the photonic device need to has its own architecture, and the machine learning, of course, has its own architecture. Why use this model? What is, I believe that, for example, Mohammed said work in the AWS, for example, and know what's mean by architecture. So you need to do this because, of course, at the final stage of our project, we will present all of the work, what we are doing at the photonic device, what we are doing at the classical machine learning team, and the quantum machine learning team. I just now I'm finishing. So if you can, yes, Muhammad, I think
Yeah. Okay. So I just have some questions. So let's start with like so these devices and all the simulations that we showed. So how accurate are these? So like if I do something, if I make a device and simulate it, like, and then I want go to the hardware. So like, is it similar? Like, what is there a difference in the accuracy?
Yes, that's a great, because if we implement the interconnect, I think that we need to simulate the loss as well. There's a popular method we can use as parameter or whatever. But I think for the sake of publishing paper, I published actually a paper using finite difference time domain only package. Because you ask a great question, because if we are about to produce our sensor, it's all about how to simulate the loss. How to simulate a loss from your device, the engineering parameters, and how to simulate the loss from the manufacturing process as well. I think the scope of the project is actually publishing a paper regarding applying different models, different machine learning models, even if it's classical or quantum. So as a photonics team, we will provide you with the data it's actually accurate regarding the design simulation, regarding the engineering design, not regarding the manufacturing one. So of course, all of our designs, if you are about to manufacture it, I think that's not related to accuracy here, because you are not simulate the loss in this process. You can use it. You can simulate the loss for different ways. For example, you can use Monte Carlo simulation or whatever. So I think, again, in the scope of this project, I believe that we need to simulate the photonic device and generate the accurate data regarding the engineering parameters only, and give you this data to apply different machine learning models to predict the behavior of the hardware itself.
Okay, yeah, makes sense. So okay, so my other question is about actually. So let me tell you what I understand from it, and then you can tell me if whether I'm right or not. So this is what I understand from your discussion about the whole project. We so there are two things that I think there are two different things. First one is that so basically we have these methods, right? We have these simulations and these things that we can just make a device. We can use a software. We can give it some input and it gives us some output. So that's basically a sensor, and we designed it on a simulation. Now, what are we supposed to do? Are we trying to eliminate that sensor? So it's like we don't even need the sensor anymore. We are just, I will just give you I don't know, artificial neural network or some kind of model, and that will do exactly what sensor or that simulation was doing. Is that what we are trying to do?
Yes, I think actually, if there is available, I think you find an available data for one of those papers. Yes, you find available data.
Okay, then.
You find it? Did you
So
find
not
it?
yet, not yet.
Yes, I think one of those papers has already published their own data. I think you can work on it right now. Actually, and actually for both teams, for the quantum and the classical, you need to work on this data to find what are the best models to apply to these data. Because we need to maybe it take about, I think, 1 week or 10 days to design photonic sensors to provide you different data. So you need to have this intuition, what data or what model suits this different data, because at the end of the day, we can apply only different machine learning models, and we can make this contribution. It's great, but we will do a biophotonic sensor, so we will design a biophotonic sensor and give you the data related to our design that will be definitely different from the data available in the provided paper. So basically, you need to download the available data and apply the same models and try to generate the same results. If you do that, I think you finish your project, because the rest of the work that you need to wait for the design, the photonic device that we designed, and we give you the data related to our design to implement different models. You will do the same pipeline, the same process, but in different models. But again, you need to document every single step from day one. I hope that I answer your question, because I try to
kind of makes sense. Let me give you the other scenario. So basically, my question was that are we trying to replace the sensor, or are we trying to optimize the sensor with the help of machine learning?
Yes, I will discuss that with the photonics team. Actually, Zainab with us, and Muhammad Waqar Amin. I will discuss that with them. I hope that we can design not only one biophotonic sensor, but more than one, maybe 2 or 3. I hope we can do that. I know it's a lot of data, but I hope we can do that. At minimum, we will design a biophotonic sensor and give you the extracted data. But all in all, it will be not so difference between the data that you are working on it right now, from, for example, the paper that related to the how to predict the optical properties. So I don't know, but the design biophotonic sensor will the extracted data from this biophotonic sensor will not actually have a huge difference from from the paper that we need to validate. So you can actually work on the data with your pace. You need to be
Okay, I think yeah, let's just start with the papers that we have. Maybe let's try to replicate them, and then maybe next week we will have a better idea of where we are going.
Okay, yes, if you download the data from one of those papers and implement the same models to get the same results, I think you did about 70% of the work, because the rest will be the same but in different data, but with different data, and of course with different input and out, but will be the same. Maybe
I think there will be slight change in the models after new sensor comes, no?
Of course. The model, I think Muhammad Usaid will. We need a confirmation from Muhammad Usaid right now. The model, the choice of the model is depend on the data, depend on the type of the data, depend of the distribution of the data. So I think he will and the machine learning teams will choose different data for different sensors. But I think at the end of the day, it will be not, there is no huge difference, the same idea.
I think if the model works, I mean, then it's just a matter of retraining. So if I have a working model, it gives good results on some kind of sensor, and then you give another sensor and we have the other data, we can retrain it on that data and then it will work. I don't think there will be like much of a problem.
Great.
Yeah.
Exactly yes. Exactly yes.
So I think the first may I interrupt? Sorry for interrupting.
No.
I think the first issue comes about designing the sensor. Obviously, this machine, let me name them as machine learning team, both quantum and classical. So I think the machine learning team, I think, will be working on modeling making the models on the old data, and I think our side will be the designing the sensor and giving the data to them, and so that they can make a better model of it. It's somewhat like that.
Yes, great. Great, you summarized it.
Yeah.
So it's actually like our architecture here, because like that exactly. We designed in the photonic team, we designed the photonic device. We choose the right photonic device, we try to simulate it, and we generate the data and give it to you, to all of you, to the quantum machine learning team and the machine learning team, to apply the pipeline from the data preparation to the deployment. So you will use different classical and the quantum machine learning, and you will analyze and compare results. And of course, you need to document every single step and make your own architecture, the architecture of your work. So I think that the significant contribution will be from the quantum machine learning team, because in this area there is no such papers, no plenty of papers related to quantum machine learning. So if they did a good job in quantum machine, and actually I basically tried to learn this skill from the quantum machine learning, and how do you choose the quantum algorithm that best suits the extracted data to achieve higher accuracy. So I think if we can did a great significant contribution in the quantum model, I think we can really publish a good paper. Yeah.
Anything I mean, anything I want to just ask something. Okay, I think from our team there is there's someone who works on quantum photonics. Can they like share some books or knowledge? I can increase my knowledge in this field, quantum photonics and photonics area.
Yes, I will share with you. Yeah,
Yeah.
if you need more example about how to simulate photonic device, that will great. I will share with you on Discord. And actually, I shared with you two PDF. The first one for
I've gone through the two papers that you have showed. I've gone through both of the papers, the theory, and I read the papers properly up to down. So I need some more knowledge on photonics part.
Right,
So
right.
please share some papers or information. I'll be very happy to.
Great. Do you see the finite element presentation?
No. I haven't gone through that. I have gone through the this tuberculosis paper. I have gone through that one. That paper I've read from. I've read that paper. But I'm going through the another one. This one. Did you show another paper? You show. I'm actually halfway through it. I'll complete it by today. Actually, I have it in my schedule.
Great.
Okay.
So I will share with you some photonics materials related to those papers. Exactly.
Okay. Surely. And if you have any books on fundamentals of photonics, much better books. I have gone through books, definitely. Much better books on fundamental photonics or application-based books. For some theoretical books on photonics also, you can share with me. I'll go through those.
Great. There is a book from Kassab. I will share it with you. But actually, the photonics field is a very big. So we
I think we should stay in our area. By a photonics sensor, we should stay in our area.
Yes. Great. I will do that. I will share with you some materials related to that. And actually, if there is any question or any thoughts about photonics design, sensors or whatever, we can share it with each other. You can ask.
Discord is open. Discord.
Yes.
And
sorry,
my network is interrupting. Actually, my network bandwidth sometimes gives a problem. I think I'm interrupting. I'm very sorry for that.
No, never mind. I believe that I think we need to share more materials about quantum machine learning. I hope I hope so. I hope to learn more about how we design. I think it's the same idea from the classical machine learning, but how to choose a quantum algorithm, and that I think I need to if one of us, I think maybe there is, I think Raja or Muhammad or you, Marjanka, I think maybe Zainab also. I don't know, but I think you have an experience about how we use the quantum machine learning and how to model a quantum machine learning.
Actually, I have experience in quantum simulation.
Great.
I worked with quantum algorithms to simulate.
I'm very sorry, but I have no experience in quantum machine learning. Classical machine learning, I do have some idea.
Me too, Muhammad.
Yeah.
I don't have any. Yes. So,
me too. I don't have really experience in QML. I have just in quantum simulation and quantum algorithms.
Great. So how can we use the available data, for example, Zainab, in the provided paper? This paper, for example, I will share it with you. This paper, from this paper. If there is available data from this paper, how can we use a quantum algorithm to model the same, or actually to get a better or higher accuracy for the same target or goal? How can we use the quantum algorithm to predict the different engineering parameters? If you have any thoughts about that, I think.
Yeah, I think we can use VQ and variational method, because maybe this algorithm. I think I need to think about and research.
Okay,
yes, right.
So I can speak from my experience. So basically, as much as I have worked, I have understood like quantum machine learning in a way of like more like optimization, right? So when we talk about classical machine learning, so we start with, I don't know, decision trees or like neural networks and stuff like that. But I think quantum machine learning is very different from that in the way that it, okay, so we basically, I think the correct word would be quantum optimization. So the models and the algorithms that I have worked with, QA, and VQE, they are all basically just, kind of solving, taking inspiration from physics. And the main part is to just, problem representation. So let's suppose you are trying to solve traveling salesman problem. I hope you guys know traveling salesman problem, right? So one person has to deliver all the cities and basically finding a Hamiltonian cycle in a graph. So what you need to do is you need to represent that problem, first of all, in a binary variable, right? So that your quantum circuits can understand that. Once you do that, then you just have to map that problem into a like Ising model. So Ising model is just coming from like physics, where you can have like spin, you have half plus spin and minus half spin. And then there is BQM, I guess, by quadratic optimization. So there are like 2 to 3 things, and like as much as I have seen in quantum machine learning, what you are trying to do is you are just trying to map your problems, whatever problem you want to solve. If it's an optimization problem, it can be modeled as a binary in binary language. You just map that problem to any of the problems that are already solved, and then you can maybe use, Qiskit has some stuff, like IBM have some really cool cloud services that you can just use their stuff and you can find your answers. So it's more like mapping problems to one another.
Yes. So if I understand you correctly, we need to simulate it using one of the. We can use, for example, AWS Bracket, or
we can use what? Sorry.
AWS Bracket.
Yeah, we can use something like, I don't know, IBM Quantum or. So if you are working with Qiskit, you can just use IBM computers. We can use Classic. I mean, there was a workshop about Classic. So it's just about mapping the problem, and then it's just a matter. We already have libraries and stuff, so we don't need to do stuff from scratch.
So great. What do you need to correct from the photonics design engineering? What do you want to correctly map this problem?
So I guess, yeah, first, okay, let me give you an example. So let's suppose, so I have worked with this like entanglement purification circuits, right? So so we use genetic algorithms for that, right? And it was an optimization problem. So it's basically that, these are your inputs, these should be your outputs, but you don't know how to get there, right? So you are trying to find the circuit, basically. I think that's something similar that you guys will be doing in photonics team. So you need to find a circuit. So what you do is you model your problem. So let's suppose I say, okay, so there are 3 gates in my problem, right? In my circuit. That's the X, Y, and Z. So what I will do, I will represent it as a binary variable. So I will just say, okay, I have like this binary digit of 3 lengths, and it has like 1, 0, 1, and the first digit means that is there an X or not. So if there is an X gate, I will put a 1, and then I will put like 0 if there is no Y gate, and so on and so forth. So once you have this is the mapping that I'm talking about, right? Now you can represent your inputs like that. You can represent a circuit like in a bit string. Once you have that, you can have your output as bit strings as well. So you know what kind of outputs you want. Now you just need to figure out that, okay, what is the correct combination? So you see, like, this is like an optimization problem in itself.
Yes, great. Like this optimization problem, yes, that I shared to you.
Yeah, something like that.
Right. So you need you need actually the equations behind that that govern the design, the photonic design. You need the equation behind it, and
we need to find how to define problem. I think it will take some time. Maybe we'll just like look at it together, and we can have different discussions. Okay, how can we map this problem? How can we represent it? And then we can model it a circuit.
Yes, that's a great question. Yeah, because actually it may change the strategy, because if we are about to use numerical or console, I think it will be very useful from the classical machine learning point of view, as you said, Mohammed. But I think if we need to implement a quantum one, I think we can, as you said, we can use different stretch. Yes.
Sure. Yeah, we can definitely. We'll experiment a lot of stuff. I was actually looking forward to like quantum simulation as well. Like, so I'm glad someone like Zainab has experience in that as well. I don't know. Maybe we can simulate something like can simulate that sensors in a quantum simulation.
Yes, and we can begin with a very simple photonic device, very simple photonic, and try to implement. Yes.
Sure. Actually, I have a question about like the choice of circuits as well. So you guys like just said that in photonics you will be designing a circuit, right? So like how I like, and this is coming from like I don't know what goes on. Is there some kind of instruction like how do you choose a circuit?
Yes, of course. If I can, yes, if I can share with you if I can share with you my screen, I can give you more intuition about what is, for example, ZMax Optic Studio. If I understand you correctly, this is a program to design the optical components from lenses, cameras, and whatever. And it's actually like Optic Studio, but numerical in the micro level, in the nano level, to optimize, to design. Yes, yeah. I need to verify my license. Okay, I think okay. I think we can make another no, خلاص. Enough. Yes, great. So I think we can do another meeting to show you how we actually simulate the photonic device. If you agree with that, I will do that.
Yeah, sure. But actually my question was that you're designing a new sensor, right? And right now you don't know how. Like, so what's the process? Like, I don't want to see like how to do it practically. I'm just asking that like thought process, like what gates to put and what devices to put there. How do you know that?
Yes, actually, if you remember this presentation, if you remember it, it's actually like this. This is the GUI from if you need to design the structure. Actually, this is the GUI for the finite difference time domain. The GUI for the finite difference time domain. So you define every detail of your design, the material, the source, the monitors, and if you need to write a script to design a new component and whatever, everything is defined in this solution, and you can extract the results. So finite difference time domain is a method to simulate this photonic device. And actually, I shared with you a presentation regarding the finite element method. Please try to try to read it. I think it will be, and of course, I will if there is a time, I will share with you how can we how can we simulate photonic device.
Sure. Okay, I will go through that.
I understand the question of Muhammad. He said like how we can design a